Let's now do some momentum examples. I have 4 to show you. And the first one is hinging off this amazing collision theory we just studied. So we have what's called a gravitational slingshot. You might have heard about this before, where we send a spacecraft out into space and it uses the gravity of the planets to accelerate and increase the speed of a space probe so it can get to its destination a lot more expeditiously. And this is actually truly an amazing phenomena. If you're not utterly amazed by how the results of this gravitational slingshot, by the time we're done with this problem, then, well, you just need to get some perspective on life. Maybe you need to get a life, I'm not sure. That probably isn't true, but you probably should play less video games with all the unrealistic phenomena going on there. This is real, and this is what we actually do. So we send a spacecraft out to, say, Jupiter, and it uses its gravity to whip it around and get it to a velocity that we just could not do with chemical energy alone, because it takes a lot of mass, chemical energy, to accelerate the spacecraft to the speeds that we need. And there's a limitation. The more mass you have, the more chemical fuel you need to accelerate that mass. And you very quickly run into diminishing returns and a limit on just how much velocity you can get from these spacecraft. And therefore, the amount of years it takes to get to its destination rapidly changes. So here we have Jupiter. Now it's incredibly massive, 2 times 10 to the 27 kilograms. And its velocity is 37.2 kilometers per second, and it's moving in this direction. All right. So it's orbiting the sun, and we're going to send a spacecraft. Here's the craft that's moving at 12.5 kilometers per second. Now these are incredibly fast speeds. Many Mach, Mach being about 760 miles an hour. So this thing is 1,000 kilograms, and it's going to collide gravitationally with Jupiter. So it's going to whip around here, and that is an elastic collision, because just like with a magnetic collision, which is elastic, this is gravitational, and all the mechanical energy is going to be conserved, and there's not going to be any frictional loss per se in this collision. So this really is a collision, and we're going to have the spacecraft that's moving at 12.5 kilometers per second whip around Jupiter and go in the opposite direction. And so it's essentially like a head-on collision and just bounces back. Now Jupiter isn't going to change any speed because of its incredible mass. All right, so how does this work? Well, in an elastic collision, we've already had the relative velocity expression. Okay, so we're going to find out the speed of the spacecraft after the collision, Vs prime. So we've learned that V2 prime minus V1 prime is negative V2 minus V1. The relative velocities after is the negative of the relative velocities before. So let's expand this and specify which objects we're talking about. Object 2 will be the spacecraft, the satellite. Object 1 is Jupiter, and so we have Vs prime minus Vj prime is minus Vs minus Vj. So we're looking for Vs prime. After the collision, the speed of, actually the velocity of the satellite. And so that's Vj prime plus Vj minus Vs. Now normally in a real situation, very carefully, the trajectory is set so that it takes off at the angle needed to perhaps do another gravitational slingshot around Saturn or Earth or some other planet and get to its destination. But let's plug the numbers in here now. Now, momentum is a vector, velocity is a vector. The signs make a big difference. Velocity prime of Jupiter, minus 37.2, and before it was minus 37.2. When a mountain hits a grain of sand, the mountain is not altered in its velocity very much, is it? Minus 12.5. Okay, so that gives us minus 86.9 kilometers per second. We had 12.5 kilometers per second. We now have minus 87 kilometers per second. You might say, oh yeah, okay, that's pretty impressive. It's about a factor of 7 in speed. Yes, that's impressive, The amount of energy it takes to get it to 7 times the speed, well, it's more than 7 times, isn't it? Let's look at the ratios. Ks prime over Ks of the satellite. That's all we're interested in. That's going to be 86.9 squared over 12.5 squared, since, of course, kinetic energy is proportional to the speed squared. So that gives us 48. That is a factor of 48. I mean, we're talking 48 times the energy it had to begin with. That would translate into a factor of 48 in mass of chemical energy, the chemicals. And actually, it's worse than that, because if you put 48 times the amount of chemical materials on the spacecraft, well, now you got 48 times the mass, and you need a whole lot more energy to accelerate that mass, as I already mentioned. Well, where did that extra kinetic energy come from? Well, it came from Jupiter. But Jupiter doesn't care. In fact, you can't really detect a change in Jupiter's motion. So like I said, you better be impressed with that and recognize that, hopefully, appreciate in any case now, how amazingly useful it is to use gravitational slingshots for solar system travels, certainly long distance satellite projectiles that we could not achieve with just strictly launching the chemical rocket directly. Let's now do an impulse momentum problem that without our newfound problem solving skills would be quite difficult. We have a discus thrower applying a complex force 30t squared I plus 40 plus 5 t in the j direction. That's the force, complex force, right? To a discus of mass 2 kilograms. Originally at rest, what's its velocity after a half a second? Well, how would you do that? Well, it's actually quite simple. The velocity after 0.5 seconds. Since force is applied, force times time is change in momentum. So that's impulse. So impulse is integral of f dt from 0 to t, 0 to 0.5 in this case. And that is change in momentum. Now, initially the velocity is 0, so the change in momentum is the new momentum. So momentum is integral of f, which is also m times v, the new v. So there it is, integrate the force. Now, to get v, just divide through by m. So we have 1 over m, and taking the integral of 30t, we got 30t to the third over 3i, plus 40t, plus 5t squared over 2j, from 0 to 0.5. And now, going through all that, we get 0 doesn't, all the terms go away. But plugging in 0.5 for t, and 2 for m, we get this, and that yields the velocity at 0.5, 0.625i, plus 10.31j meters per second. So that worked out real easily. Such a wonderful problem-solving method. Now here's a fun little problem involving a bullet shot at a block, and the bullet's going to embed itself in the block, and the block is then going to push against a spring, which is going to compress a certain distance, actually 15 centimeters. So after the bullet collides with the block and embeds itself in, the system will compress 15 centimeters. There's the masses of the two objects. So the question is, what's the initial speed of the bullet? Well, first of all, the velocity of the block, and then the initial speed of the bullet. It's asked in that order because that's the way you have to do it. Now, if you knew the velocity of the bullet, you'd say, okay, its momentum, since it's conserved, is the same momentum that the system will have after the collision. So the bullet's momentum is the whole momentum, hits the block, and then it's easy to find the velocity of the block-bullet combination. But we don't know that. We have to work backwards. So let's work backwards. First of all, find K. We have enough information for that. K is force per compression, and the force is 2 newtons. It was in the problem for a x of 0.25 centimeters, which is 0.025. So we have 800 newtons per meter. That's the K. Now, after the impact occurs, which is very lossy, when that bullet hits the block, you're going to lose a lot of kinetic energy. But once that's all done and the thing is heated up and all, which it very much does, then you've got motion. We're on a frictionless surface, so the kinetic energy translates into spring potential energy. So we've got conservation of mechanical energy after the impact. So let's work with that. The kinetic energy of the total mass at that point is 1/2 m total v total mass squared, and that's 1/2 kx squared. So the halves will go away. And now let's solve for the velocity. So that's easy to do. Square root of kx squared over m total. M total, we got to be careful about that. That's the entire mass, which is 1 kilogram now. So we got the 800, the 0.15 squared over 1, square root of the whole thing, gives us 4.24 meters per second. So we have the velocity of the mass after the collision. Now we can use the conservation of momentum to figure out, knowing what the system mass is after the collision, and momentum is conserved, let's figure out the momentum of the bullet before, which is the same. So mv0 is m total v prime. We're looking for v0, so plug in the numbers. Total mass 1, 4.24 over 0.01, the mass of the bullet, 424 meters per second. Now here's a problem involving energy and momentum. Should be pretty fun once again. So we have a frame, a 0.1 kilogram frame. It's suspended from a spring, and as a result of its own mass, the gravitational tug on it stretches the spring 5 centimeters, 0.05 meters. Then there's going to be a 0.2 kilogram lump of putty dropped from rest onto the frame from 30 centimeters. So 30 centimeters up, it smacks the frame on the bottom, and you can imagine what's going to happen. It's going to cause the mass of the frame to move in initial velocity, v0, and we're going to see how far down the entire frame goes. So we have position 1 and position 2. So we're going to use conservation of energy there. So find the initial velocity of the frame from what conservation principle? With a lump of clay comes down and smacks it. So that's going to be, it's not going to be inelastic collision by any means, so it's conservation of momentum. Then, once it's moving, find the spring stretch from conservation of mechanical energy. This is certainly not elastic. In fact, it's completely inelastic as far as the collision type. So, we have the following relationship, that the velocity of the putty as it hits the platform on the bottom can be found with the kinematic equation, rad 2gh, or rad 2gd, and then the initial velocity of the entire system, since it's a collision, an inelastic collision, is that speed times the ratio of masses. So little mass, mass of the putty, over the entire mass of the system. You can validate that with any inelastic collision and conservation of momentum on your own if you want, or just do it in your head right now. So what do we get? We have now that work done by the spring plus work done by gravity, which I think is all the work done in the system. Is there anything else? If that's total work, spring, gravity, yep, can't think of anything else, then that's delta K. So let's carry that on. And total work is delta K gives us that at position 1, K1 plus US1 plus UG1 equals K2 plus US2 plus UG2. And what is 0 here? Well, K2 is 0 because it comes to rest. Moreover, we'll set the reference frame for gravitational potential energy at the lowest point. So UG2 is 0. But I think all the others have non-zero values. So US2 is K1 plus US1 plus UG1. Now let's expand this. So K1, 1/2 of the total mass, V0 squared, plus US1 is 1/2 kx squared, where that x is equal to the 5 centimeters, or 0.05, and UG1, m plus m, g, times the distance that it's above position 2, that's d. So 1/2 k, this is US2 now, 1/2 kx plus d, it already had stretch x and also an additional d, so that quantity squared equals 1/2 m plus m. Now, V0 was rad 2GH, little m over little m plus big M. So you square that and you get 2GH times the square of that ratio, m squared over m plus big M, quantity squared. Let's go ahead and divide things out here while we have the chance. There we go. And plus 1/2 kx squared plus m plus big M GD. So what is k? K is going to give us a little trouble here. Well, it's F over x, and the force is equal to the gravitational tug, mg, big MG, and x was 0.05, so 0.1 g over 0.05. Because of the way the numbers work out, we just have 2g for k. That's going to be kind of nice to include that. Replace k with 2g. So let's go ahead and do that now. So since k is 2g, 1/2 of that is g, x plus d quantity squared, equals, we have gh, there it is, times m squared over m plus m, plus 1/2 k, 1/2 k is g, x squared, plus m plus m gd. And guess what's common to each term? Yes, indeed, the g's go away. So rewriting that expression, the first thing we add is x plus d quantity squared. So if you expand that, we get x squared plus 2xd plus d squared. G's are all gone, so we have that being hm squared over m plus x squared plus m plus m d. Now, the x squareds go away. That's very happy. I'm very happy about it. Hope you are too. And let's bring all the d's together. So here's d squared plus d. Well, we have 2x, and we have a d over here, so let's bring this m over, negative m, and this m over here, big M over to be negative big M, minus hm squared over m plus m equals 0. So you can see what form of expression we have here. It's a quadratic. It's time to plug some numbers in. D squared plus d times 2x is 0.1, m is 0.2, big M is 0.1, minus h 0.3, 0.2 squared over 0.3 equals 0. 0.1 and minus 0.1, 0.3's divide out, and we have d squared minus 0.2d minus 0.04 equals 0. Plug it into the quadratic formula, and out pops the answer we're looking for. D is 0.32 meters. I know that you think that was a lot of fun. It was very satisfying working that wonderful problem, and I hope you feel like you benefited from it.